Director, and I'm one of the co-chairs for ARCS Forward this year. For those of you that are new, ARCS Forward is the National Scholar Speaker Series, where we feature our fabulous ARCS scholars and alumni from across the country. And with that, I'm going to get us started. We have two fabulous speakers, Dr. Emily Levesque and Samantha Garza. So Samantha, I'm going to turn it over to you.
Okay, let me get my slides ready. Oh. All right, we can all see slides. We're all good. Okay. Well, hi, everyone. Again, my name is Samantha Garza. I'm a fourth-year PhD candidate here at the University of Washington in the astronomy department. And I thought for this talk, I would share a little bit about my thesis work with y'all. Let's see. Oh. There we go. So before we start, I wanted to formally introduce myself. My bachelor's degree is in physics, but I've been doing astronomy research since my freshman year of undergrad, primarily about different parts or processes of galaxies. So before coming to UW, I was a member of the National Astronomy Consortium. I worked at the National Radio Astronomy Observatory and was a research intern at the Harvard-Smithsonian Center for Astrophysics. And all of these experiences kind of solidified my love for galaxies and want to pursue an astronomy PhD, which is what led me here to UW, where I currently study the atmospheres of galaxies. Okay, so before we get into what I do, I kind of wanted to talk about why it's so important to study galactic atmospheres. So firstly, galactic atmospheres are a key player in why galaxies can have the necessary material to form stars and planets. So if there's any people that are interested in planetary science or life somewhere out in the universe or just stars themselves, like Emily, you need gas to form these stars and planets. And one way that galaxies can get this gas is through galactic atmospheres. Another important question that you can hopefully start to answer by studying galactic atmospheres is, why do galaxies stop forming stars? And we believe that that process takes place in these atmospheres, and we can get insight into solving this question. And lastly, a lot of people care about this question, which many of you might already know, which is why do galaxies and kind of material in the universe not have as much as we would think? So we have this famous chart where the visible universe only takes up about 3 to 5%, and the rest is dark energy and dark matter. And so by studying galactic atmospheres, we can get better constraints on the visible material, and so we can start making breakthroughs in our understanding of this pie chart and the matter in the universe. And so before we get to my thesis work, I did want to talk a little bit about the galactic atmospheres and give everybody a good background. So our current understanding of galaxies is that they're these giant ecosystems where material flows in and out, and the fate of this material in a galaxy is governed by the complex interplay between the gas entering the galaxy, either through galaxies merging and crashing together, or accretion flows and gas being blown out of a galaxy, either through stars forming and dying in a galaxy's disk that create these giant galactic winds and outflows. And all of these moving parts of this galactic environment are represented in this animation. And if we freeze on the last frame, we can fully see all these parts together. So we have inflowing gas from other parts in the universe in that light blue color, gas that's being blown out of the galaxy and into the atmosphere in this orange. And some of this gas actually leaves the atmosphere, but a lot doesn't have enough velocity to escape this galactic halo. So it's recycled and falls back down into the galaxy, which is shown in that pink color. And the rest of this gas that makes this atmosphere is represented in the light purple color, which is very diffuse. And I also want to note that these atmospheres are huge. So we typically think of these atmospheres as giant halos that can extend to about 100,000 light years around the galaxy. And like I've said before, these various processes are moving material around in this galactic environment. And the most interesting characteristic of this material to me is the elements that you can observe in this gas. And some of my favorites are oxygen, silicon, nitrogen, and especially carbon. And like our own atmosphere, galactic atmospheres are pretty diffuse, and so it's hard to observe. But as astronomers, we've devised a pretty cool way of studying the elements that live in this gas. And the way of doing that is something that's set up kind of like this, which we call an absorption line spectroscopy experiment. And so depicted here is a representation of that typical experiment. And for this to work, you need a bright source of light near our targeted galaxy, which most of the time is a quasar. And you can think of quasars as just basically cosmic flashlights that we use to light up the gas around galaxies. And so as this light from the quasar comes towards our detector, which is that rainbow arrow, it kind of lights up the gas in the atmosphere, and then we can detect it. And so the detector that I use is the Cosmic Origin Spectrograph on the Hubble Space Telescope. And if there's carbon along that line of sight, then that element should take little bites out of our spectrum, which is represented by this little Pac-Man. So if we set up our experiment again, we have our carbon ion taking bites out of our spectrum. This is what it would look like. So this is a spectrum from our quasar. It's passing through the atmosphere of a galaxy where we have light on the y-axis versus wavelength on the x-axis. And there's many bites or absorption features in the spectrum, including one from our little carbon ion. And if we use the area of this little curve that it makes, then we can tell how much carbon is actually observed in the atmosphere of our galaxy along our line of sight. And so now that we know a little bit more about galactic atmospheres and how we observe them, we can start to actually study them. And I want to tell you a little bit of my work, which falls into the category of trying to figure out how galaxies are keeping their stars. So one of the main parts of my thesis comes from my involvement in the survey called the Civil Survey. I've been talking about carbon a lot, and so you might have assumed that we have a wealth of carbon observations that we use, and actually that's not the case, as you can see here on the figure on the left. So this figure shows that some of the surveys that we have that have studied galactic atmospheres of a range of different types of galaxies, and for at least 2 of the surveys, there's little to no carbon. And so you also might notice it's labeled as CIV. We call that carbon 4. This just means that this particular carbon that we're looking at is highly ionized, and specifically for this ion, it's lost 3 electrons. And so we're interested in this particular form of carbon because it lives at a temperature of gas where other elements live, and it's been proven to be a very good tracer of star formation in galaxies is what we're interested in looking at. And so the amount of carbon observations available has completely changed now that we have this Civil Survey, which was accepted as a Hubble Space Telescope program. And the power of this survey is it fills this notable gap in previous absorption studies by providing a large amount of carbon coverage. And so the Civil Survey more than doubles the amount of literature sightlines that probe the inner part of galactic atmospheres of Milky Way-like galaxies, and the detections of these are shown in the plot on the right. So we supplemented these new observations with available observations, mostly of Milky Way-like galaxies, but a lot of them are from galaxies smaller than the Milky Way, but we're still interested in studying them. And this is shown on the plot on the right. So on the y-axis, we have the amount of carbon along our line of sight versus the rate at which stars are forming in the galaxy. And so since those are a little bit confusing, I'll just put them there just for us to remember. And so how we can start to study this is we separate our observations into 2 galaxy groups. The first being star forming. So if the rate at which stars are forming is greater than log 10 to the negative 11 per year, then we put them in our blue star forming group. And then we have our second group, or the passive sample, or not forming stars as much, and that's in our red group, which is anything that's forming at a rate that is less than or equal to log 10 to the negative 11 per year. And what we found immediately was that there was pretty different detection fractions for these 2 groups. So we had 72% detection fraction for our star-forming sample and 23% for our passive sample, which on its own is showing a pretty significant dichotomy between these 2 samples. But we did run some statistical tests just to make sure, and we did find that these 2 groups were definitely drawn from 2 different paired distributions at a confidence interval greater than 99%, which is amazing. And this is consistent with results found for carbon in galaxies much smaller than the Milky Way, and tests done for oxygen, which was something that we weren't expecting. And that's for in Milky Way type galaxies as well. And this is extremely exciting because it shows that our carbon, which was previously thought to live in a temperature regime that's much lower than oxygen, is actually acting something similar to oxygen. So that's something we didn't know before. So we're really interested in kind of teasing out what's going on there. And so for the last chapter of my thesis, I'm currently working on determining the exact temperature and density ranges so we can get a full characteristic and diagnostic of what's going on in these galactic atmospheres. And another main result is that with the supplemental data that our survey provided, we can now definitively say that there is a large carbon reservoir around these galaxies, especially highly star-forming galaxies. So galaxies that are no longer forming stars do not have this carbon reservoir. And this dichotomy is a key insight into how exactly this feeding and fueling process is happening in star formation or star-forming galaxies, and kind of going back to those big galactic atmospheres that we talked about in the background. And this is really cool because it can tell us more about what's going on in galaxies, how they're forming and evolving, but also our own cosmic origins, which is pretty cool, since we all have carbon in us. And I also wanted to highlight just really quickly, because this is really cool for me, that we published these results in the Astrophysical Journal Letters, and UW News thought it was pretty interesting and did a small press release about our paper, which was really fun to talk to reporters about what I do. And it got picked up and went literally all over the world, which was really exciting. And so it was just a fun experience that I got to have just recently. And before putting up my conclusion slide, I just want to say thank you to ARCS for supporting me throughout my fellowship, especially Nancy and Douglas Norberg, who are my own personal fellowship sponsors. Without ARCS, I wouldn't have the freedom to do the research that I do, but also pursue education and public outreach initiatives, which I'm super passionate about. Just to name a few, I help run Astronomy on Tap every month. This is an event where we showcase local and guest astronomers' research to the general public in a low-stakes learning environment, a local brewery. I'm also a mentor for the pre-major in astronomy program. This is a class for first and transfer students to learn essential research skills and prepare them for internships by completing mini research projects. So I've mentored 5 students throughout my time in the program, and many of them have gone on to win competitive research internships. It was super exciting to see them do that. In addition, I'm a leading organizer for eSteam, where we bring one-on-one support and astrobiology-related activities to incarcerated students in Snoqualmie, Washington. This is one of the favorite outreach initiatives that I'm a part of, and it's super cool to work with the students and watch them grow and trust you throughout the week. And it's just really great to be a person that they can depend on. Some of the best activities is when we bring labs for them, which is some of the gifts that I'm showing below. And it's just great to see them participate in science, which is really fun. And lastly, I give planetarium shows at the UW Planetarium, and I also represent UW Astro programs as a volunteer at the Pacific Science Center. I was just featured in one of their Career Corner videos, and it would have been extremely hard to be active in all of these without the support from ARCS, so I'm super grateful to have been a fellow. And with that, I will leave my conclusion slide up, and I'm happy to turn the floor over to our next speaker, Emily Levesque.
Thanks so much, Sam, and thanks so much for sharing this just completely fascinating research that you've been doing and all of the outreach work that you've been able to get to do. It's always just so incredibly cool to see research from any sort of ARCS scholar sort of results, and this is especially meaningful to me because I'm a professor here at UW. I am also a former ARCS scholar myself, and I wanted to start by sharing just a little peek at what I was up to when I was an ARC scholar. So I was an ARC scholar at the University of Hawaii back in 2009, and I actually won that year's ARC Scholar of the Year competition. And I say that, and especially after having seen what Sam just presented and how just mind-blowingly cool astronomy is, that might not sound too totally wild. The way that this competition worked at Hawaii was that individual departments would select one student to represent them, and then we would go to this lovely dinner, and everybody would take turns presenting their research. And look at what we get to present as astronomers. We get these, gorgeous pictures of galaxies and their atmospheres and how they form stars. We have these pillars of gas and dust that form stars and dying stars. And it seems like the easiest sell to convince a room full of people with a presentation like Sam's. Yeah, this is absolutely the research that you want to choose for your Scholar of the Year. And the reason this was challenging at Hawaii is because the astronomy students would present, and then right behind us were always graduate students from Hawaii's spectacular marine biology program, and they would show this. They proved that there was literally nothing in the universe cuter than baby seals and the incredible research and conservation work that they were all doing. So it came as a real surprise to actually be selected as the Scholar of the Year in the face of something this cute. But this also gets at one of the things that I've always loved about astronomy, which is that it's really not hard to get people excited about space. We just get our imaginations captured by the majesty of images like this, the fact that we can tell exactly where the carbon in our bodies came from and the path it took through the universe. These are just incredible discoveries that we love to just sort of get swept away by. And one thing that I do love is this contrast between everybody loving the majesty of space and just the sheer science of space, but not as many folks really knowing exactly what scientists do all day. I think for a lot of people, if you tell them to picture a professional astronomer, they probably picture something like this. So they probably picture a man with a beard and wearing a lab coat and standing next to a little telescope that he's peering through with his eye to, try and solve the mysteries of the universe. And one of the things that I love in my job, in addition to getting to study weird stars and how they die, is getting to sort of poke at this idea of how science works and the stories behind how it works. This picture is totally fair because it's sort of a professionalized, like lab-coated version of how a lot of us got interested in astronomy. it's certainly how I got interested in astronomy. So this is me back when I was 6, and I'm very proudly wearing my Hubble Space Telescope t-shirt, which Sam and I have now both been lucky enough to work with data from. Hubble had just launched in this picture. And I knew Hubble was a big, cool telescope. I didn't understand why 6-year-olds couldn't use it. But the telescope that I used was a little backyard telescope that my dad had been fortunate enough to buy that we would occasionally set up in our yard in southern Massachusetts. And when I imagined professional astronomy, I just pictured probably something like this. And my version of that didn't change until I was halfway through my undergrad degree at MIT. The summer after my sophomore year, I did an undergraduate research project that involved traveling out to Kitt Peak National Observatory in southern Arizona. I went there with my research advisor and I did my first bout of real professional observing. We went to this tremendous mountain, which you can see is covered with excellent telescopes, and we got to use one of those telescopes for 5 nights. And I remember getting there with my advisor, putting our stuff in the observatory dorms, and then going to sit down at dinner. And my advisor very kindly introduced me to everyone and said, "This is Emily. She's a student researcher working with me, and this is her first time at a telescope." And the whole room started going, "Oh, that's great. That's so exciting. Like, drink some coffee now so you can stay up all night, but stop at like 3 a.m. Otherwise, you'll never sleep." And then someone else said, "You're in Arizona. We know you're not from around here. You're from Massachusetts. So remember to, keep an eye on where you're stepping. We have little brown scorpions that can be very dangerous. One once crawled up someone's pant leg and stung them while they were observing." So everyone kind of picked their feet up off the floor and kept listening. Someone else said, "Oh, that's nothing. I know a guy who was observing and he had a raccoon crawl into his lap in the middle of a dark dome and he just sort of pet it and it went to sleep." And someone else said, "Well, I know a guy who was in a telescope when it was struck by lightning." And they just started telling more and more absurd stories going around the table. And I was sitting there and I think I had my fork stuck halfway to my mouth going, I can't even eat. I'm so interested in hearing all these tales of what doing astronomy is actually like. And I couldn't decide if I wanted to stay there all night and just listen to them storytell or run off to the telescope and start doing my research. And on my advisor's very good advice, we did go to the telescope and start doing research. And that work actually formed the basis of work that I'm still doing today. We were studying stars known as red supergiants. So red supergiants are very much what they sound like. They are very cold stars, so they show up as red to our eye, and they are supergiant. These are stars that are at least 8 times the mass of our sun or more. Because they are so big, they're incredibly bright. All of you have almost certainly seen a red supergiant just by casually looking up at the sky and stargazing. Because if you find the constellation Orion, it's really easy to spot because of those 3 bright stars in a line that make up Orion's belt. And you look just above Orion's belt to his shoulders, you'll notice that one shoulder is a very orangey reddish looking star. That's Betelgeuse, and it is a classic example of a red supergiant that is so nearby that we can easily see it with the naked eye. Even if you're somewhere with bright city lights or a lot of light pollution, you can almost certainly spot Betelgeuse. Now, I say supergiant to describe how big these stars are, and I wanted to give some context for this. I've drawn a little circle here that is meant to illustrate Earth's orbit and a teeny tiny dot in the middle of the screen, nearly to scale, that represents what our sun would look like relative to Earth's orbit. So to show you how big Betelgeuse is relative to our sun, we're going to need to zoom out a little bit. There's Earth's orbit and now Jupiter's orbit and Saturn's orbit. And if I were to replace the sun in this picture with Betelgeuse, it would stretch out well past Earth's orbit. It would be making it out to roughly Mars's orbit. It's enormous relative to our sun. And one of my jobs during this summer research project was focused on measuring different physical properties of red supergiants, including how big they were. Now, I get people asking me a lot, how in the world do you measure how big a star is? Do you just try to take a really good picture and measure one side to the other? We cannot get out there with a massive tape measure. What technique do you actually use to measure the size of a star? And we do this by using the very same type of observation that Sam talked about, spectroscopy, where we capture the light from a star, we sort it out according to its color, and we then look for these dips of absorption in that light caused by atoms or molecules that are absorbing the light. In the case of a red supergiant, if we were to sort out all the light by color, going from blue on the left to red on the right, like you see here, you see these great big dips or zigzags in the spectrum. all of those dips are coming from molecules of titanium oxide, which are absorbing tons of light from the star and which absorb more light if the star is colder, because you can actually make more molecules in the star's outer layers. I have a little animation of what a spectrum would look like for a red supergiant if we started it relatively warm for a star like this at about temperature of about 4,000 Kelvin and then cooled it off. As the star cools off, you see those big lines show up and then get deeper and deeper and deeper. So as the star gets colder, the lines get really, really, really strong. And what that means is that if we can observe a bunch of red supergiants, like my advisor and I got to at Kitt Peak, and measure how strong each of those lines is, we've effectively grabbed thermometers that tell us how cold the stars are. So with a bunch of these spectra, I could start filling in a big table saying, we observed this red supergiant and it was pretty hot. We observed this red supergiant and it was pretty cold. So I've just told you how we measure the star's temperature. I haven't told you how we figure out how big they are. And this is a surprisingly straightforward piece of algebra that we can do. If we know how bright a star is and we know how cold it is, we can get a guess at how big it must be. If a star is cold and fairly dim, that tells us it's probably pretty little. If a star is cold but fairly bright, it means it must be quite big. So for my summer research, I started filling in a table with a bunch of stars' names. You can see they don't have terribly exciting names, a bunch of stars' temperatures, and then by doing this math, the sizes of all of these stars. We were paying attention to the temperatures and getting ready to publish this research until one of our collaborators read through this table and said, hey, wait a minute, one of these stars is huge. It's much bigger than any other measurement we've ever made for a red supergiant. We might have just found the biggest star in the universe. And it turned out we had, much to our surprise. So again, we wound up getting to do a really fun press release and got to talk to reporters about our research. And to show you how big our new record holder was, this again is that illustration of how big Betelgeuse is relative to some of the planet orbits in our solar system. If we then replaced Betelgeuse with our new record holder, it would expand out and swallow Jupiter and get partway to Saturn. So we had measured this amazing, huge new star, and this was my first serious observing experience and my first serious research project. So I was in for life on studying and measuring big, weird stars. I went on to the University of Hawaii for my PhD. I worked as a postdoctoral researcher at the University of Colorado for 5 years, and now I'm here at the University of Washington as a professor, and I'm still working on red supergiants. And what I've become interested now is the very weirdest corners of how these stars can work, how we observe them, and what we can learn about them. And to talk about what makes a red supergiant weird, I want to talk very briefly about how they work and then how they die. So a red supergiant, just like our sun, or just like pretty much every star that we see in the night sky, is maintaining this really delicate balancing act where the star's own gravity is sort of pressing inward, and nuclear fusion, so almost a little nuclear reactor in the star's core, is resisting that push and generating energy that's able to keep the star very carefully balanced. So something like a normal red supergiant will be fusing hydrogen in its core when it's first formed, helium in its core by the time it's this big cold red star, and then it will go on to fuse heavier and heavier elements, carbon, oxygen, all the way up to fusing silicon for a few days. And this balancing act works great until the very end. And when that happens, I will show you an animation of what the red supergiant does. So we're now looking at a red supergiant and zooming in to the star's core where that fusion is happening and producing energy to counteract gravity. You'll see the colors in the core change as we go from fusing hydrogen to helium to heavier and heavier elements until we hit a point where you'll see a white core made of iron. Iron can't be fused without taking energy instead of producing energy. So at that point, the balancing act is disrupted. That core collapses in less than a second. All the outer layers of that red supergiant go tumbling after it and bounce off of it. And you get this tremendous event that we see as a supernova. And what's left behind is this little tiny dense leftover husk of that star's core. That little leftover star is something completely different. It doesn't have any fusion going on in its core. There's nothing left to fuse. it is actually supported by principles of quantum physics. The neutrons in that leftover core are being squeezed so tightly together that to squeeze them any tighter would start violating basic quantum principles. They resist that squeeze, and that quantum physics phenomenon is actually able to support further collapse of the star. So we call something like this a neutron star. What I got interested in studying during my PhD and then postdoctoral and then faculty research is what happens when you take the red supergiant as it looks when it's alive and this strange neutron star produced after it dies, and imagine a bizarre scenario where you could combine the two. This is actually something that's been predicted by researchers for years, but never been studied in detail just because it's so bizarre and because it's so hard to find. So to show you what something like this is, I'll start with another animation showing you two stars that are now orbiting one another in a binary. So they're gravitationally bound to one another, spinning around a common center of mass, and both of these are massive stars that could one day die like our red supergiant and produce a supernova. So when the first member of that binary dies, it leaves behind a neutron star. That second member will then become a red supergiant. It starts to grow. We know how huge these stars can get. It puffs up and swallows that neutron star, and that neutron star is actually able to settle to and replace the fusing core of that star without the star dying. The star is actually able to maintain looking outwardly like a normal red supergiant, but instead of a core supported by fusion, it has a core supported by quantum physics. This was predicted by two scientists, Kip Thorne and Anna Zhitkov, back in the 1970s, and it represents a totally new model for how stars could actually stay stable. So having studied red supergiants for a long time, I got really interested in trying to find and study objects like this. And the challenge comes if you look at the freeze frame that's currently on the screen, because that looks like a normal red star. And red supergiants are everywhere. So how can we possibly tell the difference between a normal red supergiant and a red supergiant that's actually hiding a neutron star deep in its core? We do that with the same spectroscopy that Sam and I have already talked about. So if we take the light from one of these stars and sort it out by color and sort it out very, very finely, we can look for individual strange elements that should only be produced in excess when there's a neutron star core in a star like this. So these are elements like molybdenum or lithium or rubidium that are very rare in normal stars, but would show up very, very strongly in something like a Thorne-Zhitkov object. These little zoom-ins show spectra of normal red supergiants, and you can see the little red lines where there's barely any light being absorbed by molybdenum or rubidium. As we searched for Thorne-Zhitkov objects, we came across one star whose spectrum did not look like this. It looked like this. The lines had gotten much stronger. There was suddenly a ton of lithium, more molybdenum than we'd ever seen in any other star, a ton of rubidium. It had exactly the chemical fingerprint that we would expect for a Thorne-Zhitkov object. So we had found this star, HV 2112, again, a very catchy name, that we thought was our first TZO candidate. And if you look at it in the sky, it doesn't look like anything. It just looks like a reddish star buried amongst a bunch of others. So it was the observations that we were able to take and those very detailed chemical profiles we were able to study that told us that this could be maybe a new model of this way that stars can exist and stay stable. So this has been really fun research to work on. And when I was sort of working on gathering all the data for it, I was going back to observations from that very first trip to Kitt Peak. And it was really fun to go back and work with my old observations. It was also really fun to go back and remember that first evening at the telescope where everybody was just telling me wacky stories and trying to sort of welcome me to the field of astronomy by telling me about coffee drinking strategies and scorpions and raccoons. And that experience had stuck with me throughout my entire career, and it actually wound up influencing the other big project that I've been working on in recent years, which was a book about what it is like to be a professional astronomer. I wrote The Last Stargazers. It got published in 2020. It was chosen as an Amazon Best Book in the Science category in 2020. And it's meant to be this big behind-the-scenes adventure through how we actually do this research. And I had a lot of fun researching this book. I asked my colleagues to tell me about some of the big observing adventures that they'd had, some of their favorite stories for how they worked at telescopes. And I got to have some great adventures of my own. One of my favorite things that I like showing when I talk about how we really do astronomy is the contrast between this picture of standing and staring through a telescope and how we sometimes actually do our research, that we will observe from places like the South Pole, which you can see in that bottom center image. We've taken telescopes to the surface of the moon. We've dragged telescopes all over our own planet to chase things like solar eclipses and study the outer layers of the sun. We take astronomical equipment and we launch it high into the atmosphere on board experimental balloons. And we did for a long time actually operate a telescope that worked out of the open back door of a specially modified plane. This was one of my favorite stories to tell in the book because I got the chance to do research on this plane. This is NASA's SOFIA Observatory. It's the Stratospheric Observatory for Infrared Astronomy. And the whole reason it exists is that we are very good at studying the light that our eyes see with telescopes on the ground. But we get light all across the electromagnetic spectrum. We see things like X-rays that are way too blue for our eyes to see, or infrared light that's too red for our eyes to see. But there's still a lot of astronomy and a lot of science in all those different types of light. By putting a telescope not quite into space, just up above most of the water vapor in Earth's atmosphere, we can actually detect infrared light that would otherwise be bouncing off the clouds or the water vapor. So we can fly a telescope up into the stratosphere, ride aboard on the plane, open the back door in this specially sealed chamber while the plane is in flight, and take amazing observations of things like red supergiants, looking at wavelengths that we could normally never detect from the ground. I got the chance to fly on SOFIA out of Christchurch, New Zealand when it was observing in the Southern Hemisphere. I actually got to go get hosted by the United States Antarctic program, which supports and runs supported and ran SOFIA's Southern Hemisphere work. We flew so close to the Antarctic Circle that we got to see the Southern Lights from the plane. It is absolutely the coolest adventure that I've ever gotten to have in astronomy. I wish I could tell like 6-year-old Emily with the Hubble t-shirt that this was what the job was actually going to entail. And this is one of the chapters and one of my favorite stories in the book because it really does set apart how we imagine astronomy happening and just how weird and wild the field can actually be. Another thing that a lot of my colleagues told me as I was interviewing them for the book was that they really wanted these stories of how we do research to be captured and written down because astronomy is changing very rapidly. Back when I was an undergraduate and I went to Kitt Peak, we sat at that telescope for 5 nights. We had a list of stars that we could add to or edit on the fly, and we were pointing at them one by one, doing our observations pretty much by hand. Nowadays, we do still sometimes observe like that. There's invaluable research that can be gotten with those sorts of telescopes, but we also have Hubble or the James Webb Space Telescope that operate from orbit. We have telescopes that don't even need people at them at all on a day-to-day basis. And my favorite example of this is a telescope that the University of Washington is a founding partner in, the Vera Rubin Observatory in Chile. Rubin is getting ready to come online this year and start a decade-long campaign to photograph pretty much the entire Southern Hemisphere sky every single night. And it's going to wind up giving us a decade-long movie of the night sky. We'll see every tiny thing that changes. We'll see a star that brightens or dims, a star that dies as a supernova, a little asteroid that's scooting through the night sky whose orbit we can track very carefully. It's going to be an incredible new tool for astronomy, but it does a lot of this automatically. The work with Rubin won't necessarily come by hiking out to the mountain and sitting at the telescope. It will be through gathering the enormous amounts of data that it produces and using things like, machine learning or artificial intelligence techniques to analyze the data. And one thing that really I tried to make clear in my book and that I love talking about in presentations like this is how diverse the research in astronomy actually is. We need telescopes that fly up into the stratosphere. We need telescopes that observe at totally different wavelengths, like the radio telescope that you see in the lower right. We need old school observing like the kind I did when I was a student and this cutting edge new observing that's going to be possible with Rubin. We combine all of these different techniques to do our research and all of these different really invaluable resources to do our research. So it's something that I always like making clear to folks that there is no shortage of questions to ask in astronomy and no shortage of different ways to answer them. So on that note, thank you all very much. I will stop sharing my screen and turn things back to Sam because I know we must have questions for each other and things to talk about our research and our career paths. I'm happy to start unless you had something that you wanted to ask right off the bat.
No, I think my one question is like, did you always have that image that you were wanting to go into space? I know you had Emily and 6-year-old t-shirt type thing, but was that like, did you always want to do astronomy since then, or like was there a deviation maybe?
So I always had astronomy as, one of my favorite careers when I was really little. People would ask, what do you want to be when you grow up? And I was like, I want to be a ballerina or an astronomer, or I want to be a firefighter or an astronomer. And for a long time in high school, I actually got very seriously into music. I was a violinist and tried to pursue it very seriously. So it was violinist or an astronomer. And astronomer just always stuck. It was a hard decision to make going to college, which one I was going to major in. But I think I ultimately realized that I could keep doing violin for fun. And it's really hard to do, stratospheric infrared observing astronomy for fun. And I'm really glad that I made the decision I did. How about you, though? I want to know how you got into astronomy.
Yeah, no, I kind of had a little different path. I was fully set on being a doctor and going to medical school forever. Like my mom has a background in biology and she did cancer research and was like really cool stuff. And like I grew up like reading optometry books and like medical diagrams. And so I was like set on being a doctor. And it wasn't until like my high school year, I took a physics class and I was like, okay, I can do physics. This is interesting. And like I grew up in Houston, so there was Space City and like I always had astronomy and space like in the background, but I was like, wait, you can do physics and study space? Like I didn't know that was a thing. And so after I learned that, I was like, all right, I'm set. Let's do it. Let's do astronomy. And like I started towards undergrad, but it was a very like fast switch from doctor to astronomer.
That's awesome. Can I actually ask you another question about
Yeah.
that? Because I always love hearing the stories of how we as astronomers or like any scientists get into their very specific thing. Like I love how focused and wonky we can get about our specialties. So what was the path once you were in astronomy that got you to galactic atmospheres?
Yeah, no, I was just really lucky. I got an internship when I was just coming out of my freshman year, and I was with Dr. Bob Benjamin, whom I love, who's retired now. But he was studying the inner arms of the Milky Way, and I was just like, we can study the Milky Way. This is amazing. And I was just like wanting to keep studying galaxies from there. And so I did another one looking at nearby galaxies, and I actually studied this galaxy right here, the Whirlpool galaxy. It's my favorite. But then so I was just applying anywhere that had anything to do with galaxies. And once I got to UW and I was like, there's atmospheres of galaxies, you can study that. And I'm like, there's atmospheres of galaxies. And so I like was super invested in figuring out what this was. And I just kind of stuck with it. I started working with Jess here at UW, Jess Work, who's now our department chair. And I just fell in love. I was like, I don't want to study anything else other than these atmospheres of galaxies. And that's the whole picture. So it was super, super cool.
Nice. That's awesome.
Mm. I kind of want to touch on like you said like how times in astronomy are changing. It's like
Mhm.
now that you're a professor and you're kind of in a mentorship role, is there like advice you would give to your students now that maybe like you just didn't receive as when you were kind of in their own role? How's like are there any changes that are happening?
Um, it's a really interesting question. It's a
Yeah.
really interesting question this week. But
No,
I think I have an answer that
literally.
applies no matter what, because I know when I was a student, I had fantastic advisors in undergrad at University of Hawaii, and there was a wonderful emphasis on like, look, you're here to do astrophysics. This is hard. We want you to have time to do your research and pay attention to that. And I was not an academic by like heritage. Nobody else in my family had a PhD. I didn't know any professors until I was taking classes from professors. I often didn't know what I didn't know. And the most valuable things that I got were like little glimpses from my advisors saying, hey, I'm writing a National Science Foundation grant proposal. Those grant proposals are 70 pages long. And just seeing a glimpse at how those proposals worked, I found really interesting. And as a mentor now, I try to make that a little more transparent to my students. And I try to hit a good balancing act between you should be doing your research, you should be learning and getting a chance to really dig into the science, but I don't want how we're funded or how we get access to Hubble or Webb or to Sophia. I don't want that to be just a mystery because once you have your PhD, you're suddenly a postdoc or you're suddenly a professor, and suddenly you need to know how to do this. So it's been an interesting balancing act of making sure that you get that very clear student experience, but that you also get the training and things that you're not necessarily taught. Sometimes it's just interesting to learn trial by fire, but sometimes having the coaching is good. Um,
Yeah,
I
I think
want to
that's really valuable.
I want to turn that question back around to you though, because I can say that as somebody who was a student in, 2006, 2010, and
Mhm.
I don't know what new things are happening that maybe we should be teaching more. Like how would you what would you like to see more from mentors, or what do you think is changing that maybe we're still catching up to these days?
Yeah, that's a really good question. Um, I think I came in like a little like a weird period because I did my undergrad kind of mostly before COVID, and then COVID hit, and then like now we've been doing grad school kind of post-pandemic, which is very much a very different world than before. But I think each kind of generation has their own challenges. I think a lot of it is a big dependence on the big data part. So like I don't have too much experience with it because I do small little datas. I mean, I had 46 observations that I showed y'all. I have friends that are dealing with thousands of data points. But I think a lot of my friends are doing that. And so I think getting more training in, yes, the funding and stuff, because the unknown unknowns are really important to figure out as soon as possible, but also getting like versatile training. So like I took classes in understanding big data sets because I didn't do personal data with it, but I knew that was kind of where the direction of astronomy was going. And so like having like a slight understanding of what AI or machine learning or like neural networks are, just because like we're going to have so much data that we don't know what to do with. And so I think having that as like an understanding would be good. And I didn't hear that particularly from any of my mentors, but it was kind of just like I saw what my friends were doing and I was like, okay, they're doing that, maybe I should be doing that too, just to like kind of understand what's going on.
Mhm.
And then I think also maybe just understanding the role of like what social media does. I know our generation grew up like specifically me, like we grew up with social media and like it doesn't necessarily have a lot to do what we do day to day, but I feel like being able to understand what to put on social media and also how you're branding your what you're working on and what your friends and peers are doing just in like a world of maybe science isn't like what everybody understands right now and just making sure that we're having like a kind of front of like this is what we're doing, it's exciting, and get also people other excited about what's happening. And so like those kind of soft skills that we kind of discussed of like background things you need to know, kind of what I
Yeah,
would hope
for
in a
sure.
mentor or should be
Hmm.
told.
Yeah.
And, yeah,
I
I'm like
I think
thinking of questions.
one thing that's interesting about that is that you talked about getting mentorship for, something like AI use or the role of social media. And it's an interesting thing to, become the professor and then somebody comes to you with the question and you kind of look behind yourself looking for the adult in the room and then go, oh, that's me. I'm the expert suddenly. And with the rapid advent of things like AI or large language models, we've been learning that as fast as everyone else. And I still remember a student asking me for the first time, like, oh, am I allowed to use ChatGPT on this assignment? And going, what is ChatGPT? Like we're keeping up as fast as we can, but it's interesting to learn things together as mentor and mentee. And it's a much more collaborative process than I will teach you this because we're together figuring out where things are going to make sense. With something like social media, it makes science communication and science outreach really interesting because it's interesting to imagine, for example, what Carl Sagan would have been had he been around in the era of social media. And he was such a stunning science communicator and he had such a large platform and he was so, the guy that many people heard from and that they thought of when they pictured a scientist. And these days, it's wonderfully egalitarian to get a platform and get a YouTube channel or get some way of sharing your science and your interests with everybody. But it also means that the way we communicate is different. Um, I wrote a book, which is a very old school way of doing things. And I'm sure that was influenced by like reading Carl Sagan's Contact when I was growing up. But I'm curious about what you found specifically from the outreach angle of social media. You've talked about all the different outreach things that you've done and whether it's, advertising on social media or just sort of getting a read on where people's enthusiasm goes. I'm curious how it's affected what you do.
Yeah, I definitely had to learn new things. So like I run the social media for Astronomy on Tap, and so I was handed over the like history of what we were doing, and I was like, okay, I like what we're doing here, but like for my own personal experience, I am TikTok scroll way too much. But so I was like obsessed with the short form media part, and I was like, can we add that to it? And so I had to teach myself how to like make videos and try to get content that way, and like watching people that I really admired do their own social media science communication. And I think it was just like really learning how to incorporate all these tiny new things or like I never knew how to like audio edit or video edit. And so that was fun to learn. And it was definitely like I felt more people were seeing that than they were my Facebook posts where we were running most of our website from and where we still run most of our website from. But I think it's just also rapidly changing. So I've had to
Mm.
keep up with the times, and I definitely do not know all of the lingo that probably would get our videos viral. But it's been a fun experience, and I still think there's a lot of value in books and talks and stuff, but I like to see this rise of the short form media and like podcasts are like huge. I listen to so many science podcasts. But yeah, I like this kind of change that's happening, and like I think it is something important that people should be, if they're interested in science communication or just in general wanting to communicate their science in a small way or just to themselves to like kind of get into.
Yeah.
But
I want to check in with the ARCS folks because I know that we wanted to leave some time for audience Q&A as well.
yep, Emily and I could yap all day long.
Yeah.
All right, awesome. Thanks, you guys. I'm going to go ahead and go through some of these questions we have from the audience. So bear with me. There's some in the chat and some in the Q&A. So, all right, first one, kind of related to the AI thing you were just talking about, Emily. And either of you guys can answer this. How are you using AI right now, and what do you see this technology doing for you in the future?
Sam, I'll let you take that first.
Let's see. Can we repeat one more time? I apologize. I I was
So,
also pulling
how
Q&A.
are you, yeah, of course. How are you using AI right now, and what do you see this technology doing for you in the future?
Okay. How I use AI right now, I don't use any like big ML or like machine learning or neural networks in my work just because I deal with such little data. I do on occasion, nobody call me out. I do use ChatGPT if I have a coding question that I literally cannot like wrap my brain around. I just like kind of type in what I think I want it to do, and then I'm like, oh, I understand. And then I fill in the code with what I already know, which has been super helpful instead of me when I was first learning code and I did not know anything about Python. I was like searching every like little website everywhere. And so like having ChatGPT has been nice. I did just go to a talk about AI in the era of astronomy a couple weeks ago. And again, it's like all that big data stuff. I really feel because we're just going to have like terabytes of information. We're not going to be able to do everything by hand and make as many advancements as we want. And so I think having these kind of tools to help us is really, really informative. But as always, like ethics and thinking that like we need to have systems in place to make sure like everything's going correctly, but I feel like it's definitely going to be used in the future, but we just have to figure out a way to do it responsibly.
Cool. I don't have a whole lot to add to that. That's very similar to what my current approach is. Yeah.
Perfect. We had a few questions, Emily, about the plane specifically.
Yep.
So one was, how did you take steady measurements over time in a moving jet? I think you kind of answered this a little bit. And then how can the plane fly that high with the door open?
I can answer both of these.
Yeah.
So the plane itself is a specially modified Boeing 747, and it's able to open the door because the telescope is in a separate sealed off chamber in the back of the plane. I actually interviewed the pilots on the flight and asked them about what it was like flying with an open door, and it was so exquisitely designed that they could open and close the door in flight, and the pilots would not notice any change in the plane's performance. And as passengers, we didn't notice anything at all. You do still have turbulence on a plane, and you imagine trying to take a picture with the telescope and it kind of doing this. So fun fact for parties, if anybody wants this, Sophia operated on the world's largest ball bearing. They had a huge ball bearing in there that was floating on a sort of like lubricant that would keep it from sticking. And the first time I hoped to fly on Sophia, it was actually a Northern Hemisphere campaign, and it was bizarrely cold where we were. And that lubricant was starting to stiffen up and freeze, and they had to scrap the flight in part because it wouldn't have been working properly and the data that we got would have been useless.
Incredible. I love that. Sam, how do you know that the carbon dark lines are coming only from your galaxy's atmosphere and not from intergalaxy gas between the galaxy and your detector?
That is such a great question. Yeah, it's a soup out there. But what's fun is we do have like specific protocols that we follow to make sure that what we're finding is as much galaxy as possible. So when we're observing, and kind of maybe have seen it on my diagram, but we have the quasar going through the galaxy, and then we also have to go through our Milky Way atmosphere. So like there's tons of stuff that we get in the spectra, But through our like combing techniques that we have, we make sure that we check off the quasar, we check off the Milky Way, we look for any interloping things that might be happening. And so this is kind of all happening per redshift. And so when you're combing through the spectra, you're putting in different redshifts, specifically for the ones that you do know, and then you comb through any possible redshifts. And then once you've completely done that, you're like, okay, everything has been identified. Let's now go to the redshift of our galaxy, and whatever's left has to be the galaxy since we've identified everything else. But it is a tedious process, and that has been most of my thesis work, is just combing through lines of squiggly data, which is it's fun but also frustrating, but it's a good time.
Awesome. Awesome. So we had a question about any favorite scientific podcasts for either of you, if you had any suggestions.
I'll confess I'm behind on my podcast listening, so I'll let Sam take the lead on that.
Oh, I love ologies. That's like my number one
Yes.
podcast when I'm walking. It's my favorite. I would love to be the host. I think she's incredible. If she's listening, please invite me. But no, she's awesome. I like amazing content and interviewing so many different types of people, and just like in such a funny way that it's the best. And then I'm blanking on my other ones right now, but specifically ologies would be my top science podcast.
Agreed. No, like that would be such a fun show to be on. They cover such cool stuff. They talk about such fascinating like little yeah, it's great.
So cool. And somebody put it in the chat if anyone was curious about the spelling for that. Okay, we have a long question here, so bear with me. If I need to repeat, let me know. Do we know what percentage of red supergiant that hosts a neutron star? Any way to find out? In addition, it looks that these special stars have rich lithium deposits. Maybe we can use them for lithium sources once our earthly ones are depleted.
This is a cool question. So, do we know what percentage of red supergiants could host neutron star cores? So, we found one candidate, maybe, and we're actually still testing that candidate. I have a PhD student working with me here at the University of Washington now on how you can possibly make stars like this, because that animation that I showed of the two stars sort of coalescing, that's really difficult to do in reality. So, they could be really, really rare, and we don't have any good guess on that, but it'll be 1 in hundreds, 1 in thousands if we're lucky. They should be pretty rare. Fortunately, there's billions of stars, so we have a lot of places to search, even if they're a little bit uncommon. The point about their rich lithium is a really interesting one. Now, stars are astonishingly far away. Even Betelgeuse, which I mentioned as this nice nearby red supergiant, is 650 light years away. So if we could travel at the speed of light, and right now we can't get anywhere close, it would take us 650 years to get to Betelgeuse. The Thornjitkov object candidate that we discovered is closer to 200,000 light years away. So going directly to the stars and grabbing the lithium isn't something that's feasible. But if we know that stars like this exist, and we know that they generate a buildup of lithium, and then they die and fling all those layers outward and spit lithium back into the interstellar medium, that gives us a slightly better understanding of how we make and how we study lithium in the universe. And lithium in particular is a really funny and really complicated element. So it doesn't mean that it's something that we could mine, but it does mean we get a slightly better understanding of sort of the origins of these kinds of elements, which is always useful when understanding how we can use them, how we can deal with resources that are rare. It's just another piece of the puzzle.
Very cool. Very cool. Great question. Okay, let's see. We have a few more. We're a little bit close to time, but we do want to answer some of these. They're so good. Someone had a terminology question. Is there a difference between astrophysics and astronomy, and what is that?
I could start, but then Sam, you can weigh in as well.
Okay.
Nah. So a lot of times they are used interchangeably. If somebody gets very technical about it, astronomy will sometimes deal with, the things that we do that are very unique to astronomy that physics doesn't do. Something like learning to use and build and operate a telescope, gathering the data and analyzing the data. And then astrophysics is using that data to get a physics interpretation out of it. But it's a very, very light distinction. There are two journals in astronomy that are both run by the American Astronomical Society. One is the Astrophysical Journal, one is the Astronomical Journal. The distinction between them is minimal at best. You'll sometimes hear people joke that if you're sitting next to someone on a plane and you want to chat, you tell them you're an astronomer because it sounds very accessible and pleasant and fun. And if you just want to sit and read your book, you say, I'm an astrophysicist because it sounds scary. But in reality, there is no, difference between somebody with a degree that says one or the other on it.
Yeah, I would totally agree. I use that on airplanes too.
Well, nice to know. Nice to know. A quick question about supernova explosions, which sound incredibly powerful and destructive. Do we ever sense their effects on planet Earth?
Cool. So the good news about supernovae is that most of them are incredibly far away. We actually have not seen a naked eye supernova on Earth since 1987. And even that one was incredibly far away. It was actually in a little satellite galaxy of the Milky Way. The last supernova that happened within the Milky Way was it's a little hard to say because there could have been a supernova happening right through the middle of the galaxy, which is really hard to see through. But the last one that we easily observed was 400 years ago. And for the most part, they're bright, and we see sort of a nice fireworks show in the sky, in that you might see what looks like an extra star that gets very bright, but there wouldn't be very immediate concrete effects here on Earth. There is an interesting quirk version of this where if you have a very unusual supernova, where a star is, say, spinning very quickly as it dies, and its core, makes a black hole and does all these sort of weird extra bits of physics, where the supernova could release a beam of gamma rays. And if a supernova like that were to happen very close and the gamma rays were pointed at Earth, that could potentially get a little dicey. But for the most part, these supernovae are far too far away for that to cause any sort of problem. Even the stars nearby that we think could do something like that are so far away that they don't really pose any risk. We mostly just get a really good light show and occasionally some high energy particles that tell us that the star has died. And even then, the stars have to be incredibly close. So it's mostly just a neat thing to observe.
Very cool. Very cool. Have room for maybe two more questions. So how much of a threat to astronomy are light pollution and satellite constellations?
I can start briefly, but I'll let Sam weigh in on this too. We have folks in the department who actually researched this in a great amount of detail. Light pollution is constantly a issue, but it's one that places are becoming increasingly aware of. There are cities that are established as official dark sky cities or dark sky sites. I did a lot of my research in Flagstaff, Arizona, if anybody's familiar with that area, and it's a fabulous dark sky city. And some aspects of this are just altering things like street lights to make sure that the light shines downward rather than upward. So it decreases light pollution and it's more energy efficient. The light is going where we need it. So light pollution is a constant issue that people fortunately know about and are trying to make efforts to improve. Satellite constellations are more complicated just because at this point they are less clearly administered and a little harder to control. And a lot of folks are probably familiar with things like Starlink from SpaceX. And Starlink is launching heaps and heaps of satellites that are meant to become very powerful communication and internet tools. But on the downside, they're also putting huge numbers of satellites into low Earth orbit that are very highly reflective and that can really wreak havoc on something like data from the Rubin Observatory. So we want to balance the fact that there can be upsides to this technology with not really putting a heap of minimally regulated things into Earth orbit that can mess with telescopes and mess with observations, because this is not something that AI can do. AI can't go through and just computationally take out the streak of a satellite passing through an image. Once that's happened, you can't see anything behind it. So astronomy is still trying to figure out the best way to move forward and coexist with efforts like this that could really dramatically change how we do astronomy.
Yeah, I would agree with what Emily said. I did go to a panel recently. I was at the American Astronomical Society meeting, and we were talking about science policy and what people can do to advocate for dark skies and for these types of satellite images. And there was always just kind of like, go talk to your representative if you can, or tell them that you're interested in wanting these kind of dark sky initiatives, because that always helps, one, just energy efficiency and like making our area nice, but also helping astronomers. And that's always something you can try to do.
Awesome. We had a few more. Somebody asked if there was a way to make satellites non-reflective that could help. I don't know.
I know this is something that they've looked into. I actually don't know the latest update on how successful it's been. And part of the challenge there is where you combine scientists who are studying things for, the love of discovery with companies that have to make sound use of their resources and sound investments. And if it is an additional expense to make a satellite non-reflective, there has to be a tangible argument as to why. And we hope that the tangible argument is it makes the sky nicer. And depending on how hard it is to do and how successful it is, that's a decision that's ultimately up to the private company. So it's exactly the idea that we're exploring, but it's more complicated than it sounds to implement.
And we'll just do one last question for our undergrad folks who are joining us. What would be a good industry association for an undergraduate astronomy and astrophysics student to join?
Ooh, industry, like for like with an astronomy degree, what you could get into?
Yes. Yeah, I
so
think
many
that was
things.
their context. Yeah.
I think now a lot of astronomy programs are like implementing coding learning into their programs, which is always amazing because that's how we do a lot of our research. And so you have a great coding background, you can go into software engineering, like to the tech world. I know that a lot of PhDs have also gone into law, like because they're really good at just like understanding things and like wanting to get into that kind of space law type area. I know some other people that are interested in science policy. One of them is me, but you have definitely some of the skills that you need to like be an advocate and getting into that kind of legislative realm. What else can you do? Emily, do you have more?
I think they were interested in the different things that you could do with a degree and also associations that you can join in the meantime. So there are student memberships to things like the American Astronomical Society. I'll also plug the Astronomical Society of the Pacific, which is an excellent professional organization and one that we interacted with a lot at the University of Hawaii. Things like the Society for Physics Students are great. There's student associations that particularly target students from underrepresented backgrounds in astronomy. So I would absolutely join all of those. They have great conferences. It gives you a direct line to some of the big conferences that happen every year. So look at some of the professional organizations in astronomy, and a lot of them will have student memberships.
Awesome. All right. Well, I think that is going to wrap it up today. Andrea has popped back on to give us a little goodbye message, but thank you guys for answering those questions.
I just want to say thank you to everyone who joined us today and for our fabulous speakers. And for you, Rebecca, as well. At ASG, we certainly couldn't do it without you. And this program was recorded, so we will send it out to you if you want to share it with others in your chapter or your friends or fellow students. That will be coming via email, and we hope to see you next time. Thank you so much.